Recording in progress.
Yeah, campaign everyone. Let's start off. Just give me a minute. This was the last thing that we did. Let's go ahead with one more problem. Let's get this. Point 729. No, right? 0.729. Okay, let's see. So the question is there in front of you, right? Exam में होगा, going to ask. Read the question, understand. So unless someone tells you what is happening, you won't do. To try, exam and only be there to help you guys out. Let's see. So first of all, what is the energy of the photon? One two four zero zero by 4,000 angstroms. That is 3.1 eV. Now, see, this is the energy acquired by the electron inside the lattice. Now, if you remember, I did tell you this. Whenever the electron absorbs the energy, there is no guarantee it will come out directly. It will be colliding inside and then it will come out. Now, understand one thing. What is work function? The amount of energy required to escape the lattice. Now, whenever I give you energy, and if you're colliding, so you are losing energy before leaving the lattice, isn't it? I hope you're getting it. You're losing energy after leaving the lattice. You don't lose energy, after before leaving the lattice, not after leaving it. So in this, he's saying every collision you lose 10% of the energy. So after first collision, so the electron gained this much energy and still it didn't come out of the lattice. After first collision, the energy of the electron, it will lose 10%, so it will be 0.9 times 3.1 eV. After second collision, energy of the electron, so it will lose 10% of whatever you have. So it is again 90% of whatever, this 0.9 square into 3.1 eV. Now the electron is this much energy and now it is trying to escape the lattice. Now the Ke max will be energy of that electron minus work function. Are you getting the difference? Think about it. If the electron comes out, it is going to collide with what? If the electron is coming out of the lattice, he's saying 10% of the extra energy is lost to the metal in each collision. If the electron comes out of the metal, who is it colliding with exactly? Are you getting the catch? So you're losing energy even before coming out of the lattice. So this guy would be 0.9 square, that's 0.8. Two 2.511. That comes out to be 0.31 eV. Check it out. There, yeah. Is that clear? What about the second part? Under the same assumptions, how many collisions the electron will suffer before it is unable to come out of the metal? You should have read the question properly. At least the second question would have given you a hint was what you guys were thinking was wrong. Patience. Why are you guys in a hurry to answer? Think. You got a minute more. Let's see. Right there, yeah. Right now, yeah. Now, if you see here, after every collision, you're losing 10%. So after n collisions, the energy of the electron will be 0.9 to the power of n into 3.1 eV. If this becomes less than the 2.2 eV, the work function, electrons won't come out. You can actually see if you put n is equal to 1, 9 3 is 27, 2.7 it works. If you put 0.9 square, it is 0.8, 8 into 324, that also works. 0.93, that will be 9 into 9 into 9, that's 0.729, that's 0.73. 73 into 3, that will be, I think still it works, I guess. I think n is equal to 4, it doesn't work. For n greater than equal to 4, the energy of electron is less than 2.2 eV. Therefore, 3 collisions. You could have checked this manually anyways. Clear with this? So be careful, the collisions are happening inside the lattice even before coming out. Next thing. Let's get this. Let's see. So, I hope everyone understood the question. I think few words are missing here. The wavelength, the power incident on the sheet, and the time interval from initial efficiency. So he's saying we have a wavelength which is varying from lambda 3000 plus 40t. So it's changing with time. The power incident is always equal to 100. The signal is switched on and switched off for a time interval of 2 minutes. So 2 minutes it is on and 1 minute it is off. Each time the signal is switched on, lambda starts from 3000 angstrom. So this thing is going to repeat every 3 minutes. The cycle is going to repeat 2 minutes on, 1 minute off, then again 2 minutes on, 1 minute off, and so on. And every time you switch it on, it starts from t is equal to 0. Great. The work function is 2 eV. So the work function is 2 eV. Now, if you take the lambda of the photon, that would be 12400 by 2 eV will give you 6200 angstroms. That means as long as the wavelength is less than 6200 angstroms, remember, higher the wavelength, lesser the energy. So the photoelectric effect happens. For lambda less than 6200 angstroms. So 6200 will be 3000 plus 40t. That turns out to be 80 seconds. Means from 0 to 80, there will be a photoelectric effect. From 80 to 120, there will be no photoelectric effect. And 120 to 180, there is no light only. There will be no electron emission. Clear with this? So that is the first thing you need to realize. And the power is 100 watts. Once you got this, so for the time interval between 80 to 0, the photoelectric effect happens, or electrons come out. For T between 80 to 120, lambda is greater than 6,200 angstroms. Therefore, no photoelectric effect. And T between 180 to 120, there is no light only. Therefore, again, no electrons. Right? And then if you look at this power is nothing but energy per second. So that will be number of photons per second into energy of the photon. So that is nothing but dN by dt. Power is 100 watts, but he said only 1% of it. So 1 by 100, he said efficiency is 1%. That would be, this is your dN by dt. Energy of the photon is nothing but hc by lambda. So we get dN by dt is 1 by hc lambda, which is 3000 plus 40. It's a linear function. So if you try to plot the graph, so this thing is only valid till 80 seconds. So when t is equal to 0, it is not 0, it is starting from somewhere here. It increases till 80 seconds. And then it becomes 0 till 180 seconds. Then again it starts. Then again it decreases. And so on. The cycle just keeps going on forever. Clear with this? For t greater than 80, dN by dt is 0. There will be no electron emission. And the efficiency of photo emission is 1%. So yeah, whatever energy you are giving, and that only there is a. I think I did something wrong here. Wait. This will be the number of photons per second. Actually, answer will come out same. And dN by dt will be 1 by 100 of number of photons per second. So for every 100 photons, only one electron is coming out. It is same thing as saying, out of 100 watts, only 1 watt is actually generating electrons. Clear with this? Again, if you see the questions are not tough. If you see there's only one formula in photoelectric effect. Energy incident is equal to work function plus Kmax. You just have to keep playing with that. Any doubts on this? Next one. Clear now, Ojas? Kritik? Tanvi, got this? Tanvi, clear with this? Yeah. Find the work function of the metal and state whether the current is equal or less than saturation. Let's see. Work function is fine. What about the saturation current? So here, if you look at this, photons of energy 5 eV are incident on the cathode. This battery here, which is 5 volt, so battery gives additional 5 eV to all the electrons. Means with whatever energy you come out of the emitter, everyone gets 5 eV extra. ठीक है. So energy incident is work function plus Kmax. Now all electrons at emitter right have energy in the range of 0 to Kmax. Isn't that the meaning of it? Everyone will not have Kmax. Now when they reach the collector, everyone should gain extra 5 eV. The electrons should have 5 eV to 5 plus Kmax. So the fastest electron will have 5 plus Kmax. The guy who started with 0 would have been 5. And now you're telling me it is given in the question. So the maximum energy is 8 eV. So 5 plus Kmax is 8 eV. Kmax is 3 and work function is 2 eV. That's great, problem solved. But now if you notice something, look at the minimum. The problem is the minimum. In the question, it is mentioned, it is given the kinetic energy of the electrons at the collector. Minimum is 6 eV. It is given electrons at collector have minimum kinetic energy of 6 eV, whereas we are expecting 5 eV. What is the meaning of that? Every electron that had energy from 0 to 1 eV at the emitter, they couldn't reach the collector, isn't it? Maybe because of the electron cloud, or maybe because of repulsion, or whatever is the reason, electrons who have had energy from 0 to 1, they didn't reach the collector. Is that making sense? If every electron had reached the collector, then the guy who started with 0 also would have reached the collector. And then the energy would have been 5 to 8. Is that making sense? So this implies all electrons at emitter with energy 0 to 1 eV didn't reach the collector. And if all electrons didn't reach the collector, means the current is not saturation. That's the definition of saturation current. Current is less than saturation. It's a decent question. Matlab, you have to logically figure it out. All clear with this? Any doubts on this? Next thing. And then if you see these questions, right, none of them are like really out of the world or tough, but you need to think a bit. So that is the thing. For all these chapters, right, you need to do at least for each part. Like I said, there are 5 parts, isn't it? For each part, you should do at least around 50, 60 questions so that you can cover all the models. Get this thing, this is an easy one. See? So here exactly what is happening. So if you take the sphere and when you're shining light on this, photons whose energy will be 12400 by 4000 angstroms. That would be 3.1 eV. Because of this, the electrons which are there, they start escaping. But as the electrons start leaving, the shell starts becoming positively charged. Getting it? This thing starts acquiring some charge. Now this positive charge will start attracting these electrons. Initially, electrons have more energy, so they will escape. But as the charge keeps on increasing, at some point, when the charge potential becomes equal to the stopping potential, the electrons which are trying to go out, they will start turning back. Is that the meaning of photoelectric effect? Photoelectric effect will not stop. The electrons will just not go away anymore. They'll start coming back. So the electrons will turn back when potential of the shell becomes equal to the stopping potential. So that would be energy incident is equal to work function plus E into V stopping potential. That's 3.1. This is 1.2 volt. They can ask you the charge also. That will be KQ by R. R is not given. If they're given you R, you can even find the charge on the shell. That will be the maximum charge the shell will acquire. Clear with this? Let's see one more. So that is the idea there. Once you reach V stopping potential, you will turn back. And just write that function here. E is that electric field, which is A plus 1 plus cos omega t cos omega naught t. Read. Let's see how we'll do this. Let's see. Now, first thing, if you remember, we say, right, light is nothing but an electromagnetic wave. Then that means if it is a wave, that means it has an electric field. So when you say the frequency of light is F, exactly what frequency are you talking about? So that frequency actually belongs. Do you guys remember the definition of a wave? A wave is nothing but a property that changes with position and time, isn't it? Now that property can be electric field, displacement, pressure, or anything. So when you say electromagnetic wave, in that the property that is changing is your electric and magnetic fields, right? And these electric and magnetic fields are oscillating with the frequency F. That is the frequency of the light. I hope you're getting it. So whenever you use the word frequency of light is so and so, what you're talking about is in that light, there's an electric field and magnetic fields are oscillating with the frequency F. Are you clear with this? So this is a pretty good question. So if you split this into parts, so this will get A cos omega naught t, A cos omega t and cos omega naught t. Now, if you guys remember, the wave, right? The function is something like, A sine kx minus omega t or A cos kx minus omega t ka form, right? It should be a single sine or single cos function. So you need to split this into as many simpler functions as possible. This guy will be A by 2. I think this is cos omega plus omega naught t plus cos omega minus omega naught t. That means this function which is given is actually not a single wave. It contains 3 different light waves. Getting it? So this whole function is a combination of 3 light waves. And the frequencies are omega naught, omega plus omega naught, and omega minus omega naught. And you can clearly see this is your highest frequency. Therefore, the frequency will be omega plus omega naught by 2 pi. So this guy is going to create the maximum kinetic energy. And that's it. That is the whole idea in the question. So the question is, what is the maximum kinetic energy of the electrons? If you're sending 3 photons of different frequency, the one with the higher frequency will create the maximum energy. So there was a question like this in JE once. They said y is equal to something like this, 10 cos square t sine 1000 t, something like this. The question was, this is made of how many waves? So if you actually split this, you will actually get three parts. You need to get in the form of a sine power 1. So it is actually made of three waves. Clear with this? That's a bit about the photoelectric effect. So you can go on and on, but I think that is the main theme in all these questions. If you see all placing with that only. So here we are just using the concept of a wave. So when you say frequency of light is f, understand that is the meaning of it. A light beam, when it is traveling, there's a fluctuation of electric and magnetic fields, and they're changing with a particular frequency. That is the frequency of light. The next thing is your Bohr's model. Now, before jumping into the Bohr's model, we have the Rutherford alpha scattering experiment. We don't have the full thing, right? We already did in chemistry. So we will just stick with there is one important formula there. So when we bombard, a thin gold foil. Do you guys know why Rutherford used gold foil? Because he's rich. I didn't need to use this thing. So basically, gold has a property, right? You can make it into a very thin sheets. So you can make it into very thin sheets, and so when you are trying to, send alpha particles in bombard, you don't want a thick sheet. So you can actually take a 1 gram gold and you can make it into such a thin sheet as big as your floor, the room you're sitting right now. That is the reason they use it also in sweets and all. Remember gold covering? They make it a very thin wafer and they cover sweets with that. So with alpha particles, right, and we observe most of the particles go undeviated. And some have large deviations. So whoever gets deflected, they have pretty large deviations. And this was the thing, like Rutherford model, right? So he explained, this can only happen if the entire nucleus was at one place. This could explain that J.J. Thomson ka that watermelon pudding model or whatever. So we have the nucleus. If you send an alpha particle, this is how it is going to deviate. This is your theta. And if you look at the shape here, the shape is actually a hyperbola. We have done something like this in electrostatics. Not exactly the same. You guys remember this question? Two charged particles are projected towards each other and they deflect. So if you see, they do go something like this in hyperbolic form. So let's see, there are a few things here. This is P, which is your impact parameter. Theta is angle of deviation. B is your impact parameter. Basically, that is a perpendicular distance, but the formula is not important. No need to remember all this thing. There is only one important thing which is there. Z1, Z2, E square by 8 pi epsilon k cot theta by 2. K is your kinetic energy of the alpha particle. Now, if you just combine all this, we have a formula here, which is n of theta, which will be n naught t by 16 e square by 4 pi epsilon z1 square z2 square by k square sine power 4 theta by 2. So again, there is a formula like that. Then z2 is the charge of the z square, and this is z alpha square. Z alpha ka charge basically 2e. And that is not important. So in this, the main formula is this. So what is n of theta? N of theta is the number of particles that are deviated by angle theta. No need to remember that formula. So this is the main thing. They had asked questions on this. So n of theta is proportional to 1 by sine power 4 theta by 2. Questions have been only on this formula generally. So remember this one. Another thing, if at all they can ask you, n of theta will be proportional to t. T is the thickness of the slab. Z1 is the atomic number of the nucleus. Z alpha is nothing but 2 times E. So n of theta will be this by k is the kinetic energy and z square. They never asked anything on this, but just in case. So there is a question like this, which was asked once. Find the ratio of alpha particles scattered by theta is equal to 90 degrees and theta is equal to 120 degrees. This would be sine power 4, 120 by 2 by. I think this was asked in CET or bits, I don't remember. Maybe CET only, I guess. There. That's it. You should just know that power ka thing. So Rutherford model, at least at a physics level, we don't have anything more than that one. Clear with this? And rest of the thing is chemistry only. Next thing, Bohr's model. Like I said, the theory, right, will look similar to whatever, it is the same thing, what you learned, but the kind of problems we'll do will keep changing. So listen to this carefully. The derivation is important. If something changes, you always have to go back, and physics may, it'll always change. Bohr's model of hydrogen-like atoms. So the first postulate, electrons around the nucleus. Electrons revolve around the nucleus. In circular orbits. Second postulate, the angular momentum of the system is quantized. So if someone asks you what is the second postulate, angular momentum is quantized. Don't say mvr is equal to nh by 2 pi. That is actually not always true. You will see later on. That is, electrons can only occupy specific orbits. So this mvr is equal to nh by 2 pi is actually a special case. Now, if you see how we got this also, right? We had a discussion about this in stationary waves. You can rearrange this, which is 2 pi r is equal to nh by mv. And h by mv is nothing but n into lambda de Broglie. You can clearly see that means the circumference is actually forming an n lambda construct interference. Or you can say it is forming a stationary wave. And what about the energy in a stationary wave? Energy in a stationary wave is constant. So if you see, that was one of the postulate. Rutherford model had a drawback. According to classical theory of electromagnetism, when an electron is accelerating, a charged particle accelerates, it emits photons. Remember the statement? There's a statement like that. Then the drawback goes like this: since the electrons are going in a circle, they have a centripetal acceleration. That means the electron should keep emitting photons, and eventually they should collapse. That was another drawback of Rutherford's model. Then Bohr's theory, right, explains that with the help of a stationary wave, basically. So because they form stationary waves and the energy is constant, that is the reason electrons occupy specific orbits. They cannot go into any orbit they want. This idea is important. They do make advanced paragraph questions based on this. The third postulate. While revolving around the nucleus, the electrons do not lose any energy. It emits energy in the form of radiation. When electrons transition from higher to lower orbits. There, these are your three postulates. Same stuff what you studied in chemistry. Now, the main thing. So when you do the derivations, right, this is always the common thing. There are only two equations every time in a derivation. The nucleus ZE, you did the same derivation in chemistry, but maybe then you didn't realize because you didn't know electrostatics and everything. So this will get attracted by an electrostatic force K, Q1, Q2 by R square. Since it is going in a circle, there'll be centrifugal force mv square by R. So remember, whenever they try to modify anything in this Bohr's theory, one, they'll mostly mess up with the force. So maybe they will say tomorrow the force is an hypothetical force which is equal to minus K by R power half. Find the radius of the nth orbit. So if they change something like that, you always have to come back to the derivation. So this is KZE square by R square is equal to mv square by R. This is equation 1. Second thing, angular momentum is quantized. mvr is equal to nh by 2 pi. That's it. You have only these two equations. So if they change anything, you always have to come back here. So let's try to derive the velocity and the radius. So v is equal to nh by 2 pi mr. Take this thing and put it in equation 1. We get kze square by r is equal to mv square will be n square h square by 4 pi square m square r square. We end up with r is equal to n square h square 4 pi square m square kze square, and k is nothing but 1 by 4 pi epsilon. So n square by z, that is 1 by 4 pi epsilon, so epsilon goes up, 4 goes off, 1 pi will be left out, n square by z. If you substitute the values of the constant, that turns out to be 0.53 angstroms. And this is the formula you studied. But you should know actually what terms it depends on. Now, it's difficult to remember this, but you can derive this in a minute. Once you got the radius, take this and put it in the velocity. We get v is equal to nh by 2 pi m r, which is again h square epsilon pi m e square n square by z. This thing turns out to be m will cancel, e square, h will cancel, 2 epsilon h z by n. This is the 2.18 into 10 power 6 into z by n meters per second. Now, why is it important that you remember in terms of m and n and everything? Because they'll frame a question of this sort. They will say, in an hypothetical atom, if the mass of an electron is doubled and the charge of an electron is tripled, find the new radius and new velocity. If they change something like this, you'll be gone. If you just remember 0.53 into n square by z square, you won't understand what to do. If charge is tripled, you can clearly see the radius r is actually proportional to 1 by me square. So if you make the mass double and the charge triple, then the new radius will become r rolled by 18. Isn't it? Similarly, if you look at the velocity, v is proportional to e square. So it only depends on the charge. So the new velocity becomes 9 times the old velocity. Are you clear how they'll frame questions? Or they can ask something like this. It is observed, in the calculation of Planck's constant, there's an error of 0.1%. Find the error in calculation of radius. R is proportional to h square. Then you know how to do the errors. dr by r is equal to 2 times dh by h. So they will play something like that. They will start messing up, the h ka value, m ka value, e ka value. Or they can even say something like this. In a hypothetical universe, right, the space between the nucleus and the electrons is filled with a medium called ether. And ether ka dielectric constant is 5. Find the new radius. So that epsilon naught will become epsilon medium, isn't it? Now that will become 5 times epsilon naught. So the radius will change again. So you can really play around everything. So if you just mug up these numbers and if you don't know the actual thing, and if they change something fundamentally, right, the mass or Planck's constant or something, they never asked anything like that, but they can. Mains may generally they won't, but advanced may you never know. Clear with this? You can put on the things in the red box if you want, in case you don't remember. But at least you should know that n square z to that to standard. But if they ask in some in terms of m and this thing, you need to figure it out. Clear? Now let's see how they'll ask these questions in physics. An electron is orbiting in the nth orbit of hydrogen-like atom. Now we studied in current electricity, if a charged particle goes in a circle, it behaves like a current loop. So the current due to the electron is proportional to n power x and z power y. N is the principal quantum number and z is the atomic number. So find x and y. Now if there's a current loop, that means there's also magnetic field. So this electron creates a current and that current creates a magnetic field at the center. The magnetic field is proportional to, again, n power x and z power y. Find x and y. And if you have a current loop going on there, then there's also magnetic moment, NIA. The magnetic moment of an electron in the nth orbit is proportional to n power x and z power y. Find x and y. This is how they'll frame questions. This is what I keep saying. If you see modern physics, now you will learn the chemistry topics, but we will bring everything that you learn, mechanics, fluid, everything questions will come. Let's see how to do this. And they did ask a question of this sort. The question was, an electron is going in the first orbit of hydrogen atom and another electron is going in the second orbit of the hydrogen atom. Find the ratio of magnetic field created by them at the center. That was the actual question. This is even better. Let's get this. Try. I'll give you 2-3 minutes. 2 minutes. Let me show you one. Look at the first one. So if a charged particle is going on a circle, then the current will be, someone got -3, 2. Yeah, I think few got it. Let's see. I think we got it. So current due to a charged particle is nothing but charge by time. Time is nothing but 2 pi r by u, which is equal to qu by 2 pi r. This is the first question in current electricity. The charged particle is going in a circle, find the current Q by 2 pi r by U. That means this is proportional to velocity by r. And we know V is proportional to Z by N. R is proportional to N square by Z. Yeah, done. Substitute here. So this will be I is proportional to Z by N and R is proportional to N square by Z. So this will be N power minus 3 into Z square. X is minus 3 and Y is 2. This is how you're supposed to do. Can you try magnetic field, magnetic moment? I'll give you a minute more. I think right, Nikhil, right, Advait, right, Palak, Navya. Yeah, you guys got it. Others, try. You got a minute. These are pretty good main level questions. Let's see. Now, since I know the current, what is the magnetic field? So the magnetic field due to a current loop is given by mu naught I by 2R. And this is proportional to current by R. Current is already N power minus 3 Z square and R is nothing but N square by Z. This will be N power minus 5 and Z cube. So the question which they asked, right? Electron is going in the first and the second orbit. The ratio is 32 times. What is the magnetic moment? Mu bar is nothing but number of turns current into area. That will be NIA is pi R square. So proportional to I into radius square. I is N power minus 3 Z square and radius square is N power 4 by Z square. Proportional to N power 1. See, actually you can do it even faster if you remember this concept. The magnetic moment mu bar is given by Q by 2m into L bar. Yeah? And we know from Bohr's postulate, angular momentum L is nothing but mvr, which is nothing but nh by 2 pi. So you would have got it directly if you have realized that. Clear with this. Next thing. Now, if you have velocity and radius, then you also have energy. Now, if you remember, this electron will have two energies. One is your kinetic energy and one is your electrostatic potential energy. The total energy is potential energy plus kinetic energy. Potential energy is minus K because it's an electron. ZE, E, so that will become ZE square by R. Kinetic energy is half mv square. But if you remember, we already know K ZE square by R square, that is a force, is equal to mv square by R. If you substitute here, this minus kZe square by R, this will become plus kZe square by 2R. Therefore, the total energy will be minus kZe square by 2R. And if you see here, we get a pretty good ratio here. This thing, right, you encountered in gravitation. The total energy is to potential energy is to kinetic energy. This will be in the ratio of -1 is to -2 is to +1. You guys remember this? This was done in gravitation. Energy of the satellites. Same logic we used. It works. Then K is nothing but 1 by 4 pi epsilon z square by 2. And what is arc value? Again, remember that arc from the beginning, we had to bring this up. H square epsilon pi me square. N square by z. So if you rearrange this, z only. This thing turns out to be minus me power 4 z square by n square by 4 to is 8 pi goes off h square epsilon square there. And this comes out to be minus 13.6 eV into n square by z square. So you should know your derivations, because if they mess up something fundamentally, then you will not understand how to handle the question, and which we are going to do later on. So you will need that. Clear with this? Take a break. Come back by 7 to. We'll continue from here.
So isn't it z square by n square?
Z square by n square. Hana. What happened?
So in the last line you put in n square by z square.
So this Z will go up, Nareg. What are you doing? Okay, last line you're saying. Yeah. I wrote wrong. Yeah. Chalo, come back in 10 minutes. Chalo, let's start off. So if you look at the energy levels of the orbit, so as you keep going higher, right, the energy levels actually become smaller. At least remember the energy levels for the first 3 orbits. It will be easy during the exam. So the first level will be minus 13.6 eV into z square, minus 3.4 eV into z square, minus 1.51 eV into z square. So this transition will give you 10.2 eV. This transition will give you 12.1 eV. This much you should have an idea. And whenever this electron jumps from N2 to N1, the difference in energy becomes a photon. So energy of the photon will be En2 minus En1. This is hc by lambda, and this will be, if you remember the energy formula again, minus me power 4, 8 h square epsilon square. Just remove the minus sign, and this will become 1 by n1 square by 1 by n2 square into z square. If you rearrange this, you will end up with 1 by lambda will be Rydberg constant into 1 by n1 square minus 1 by n2 square into z square. So this Rydberg constant is actually given by me power 4 by 8 h cube epsilon square c. What is the Rydberg constant value? 1.097 to 10 power 7, something like that, no? Anyone remembers? I forgot. I think it is, yeah, something of that sort, 1.01 into 10 power 7. I think there is one in meters and centimeters also, I guess. This is in centimeters, right? Or meters? This is in centimeters or meters? Per centimeter or per meter? Per meter. There. That is something like that. So remember that Rydberg constant. You'll understand why I'm being so specific every time I'm writing, how you derive this. Because they're not going to ask you direct questions like chemistry. They will mess up advanced may, they will bring stuff, and you need to know. Clear with this? Then we have emission spectrum. So in total, if you see, there are 4 formulas: R, velocity, energy, and Rydberg constant, this 1 by lambda thing. Emission spectrum. So when a gas is heated, or when you pass electricity, or you do some kind of, when you gas is supplied energy, you can do this by heating. That's the most common way. Or even if you pass electricity, even then it works. The electrons are excited to higher levels. Due to atomic collisions. And when they de-excite, they emit specific wavelengths. That's why we also call this thing as characteristic spectrum. It's like every human has a unique fingerprint. Every element has a unique wavelength. Did you guys ever think about this? How did we figure out that sun has hydrogen and helium? No one has gone there to take a sample, isn't it? So when you actually measure that wavelengths which are coming from that, we noticed, there's a particular frequencies are in more intensity than expected. And when you actually go and check it out, these frequencies match exactly with hydrogen and helium. So here, if you take n1 is equal to 1 and n2 will be any other orbit, this is your Lyman series, which is UV rays. This is visible light Balmer series. And the other stuff. Passion, bracket, P-fund. This is all infrared. This is your emission spectrum. This they emit only specific wavelengths. Similarly, absorption spectrum. If you send all wavelengths through the gas, we observe some wavelengths are missing. So basically, we know the electrons will only absorb a certain specific wavelengths, which are exactly required for the electronic transition. Right. So basically, again, these are the same wavelengths which will be missing. Clear with this? Yeah, that's your complete theory of Bohr's. Let's see if you have questions on this, and we'll see more variations. Let's see how they'll frame questions in physics. If potential energy of an electron in the second orbit of hydrogen atom is taken as 0, find the total energy of the electron in the first orbit. Now, if you guys remember, whenever you have two charged particles Q1, Q2, the energy is given by K, Q1, Q2 by R, assuming the potential energy at infinity is 0, isn't it? That is a reference line. We choose infinity as 0, and then you get the potential energy K, Q1, Q2 by R. Understand one thing, potential energy is not defined if you don't have a reference. Potential energy difference is always same. So when you use the formula K Q1 Q2 by R, you are choosing infinity as reference. But for some reason, you are messing it up, and now you're saying the second orbit of hydrogen atom is taken as reference. Then what will be the total energy of the first orbit? Let's get this. Let's see, 13.2 near. So n is equal to 1, n is equal to 2. If you look at this, in the first orbit, the potential energy will be minus 27.2 eV. Remember, double the total energy. The kinetic energy will be plus 13.6 eV. When you add them, the total will be minus 13.6 eV. So this is the ratio, minus 1 is to minus 2 is to minus 1. So the total energy and the kinetic energy have same magnitude. When you go to the second orbit, this guy will be, the potential energy is minus 6.8 eV. The kinetic energy is plus 3.4 eV. And potential energy at infinity is 0. So now you're shifting your origin, right? You want to make n is equal to 2 as 0. So how do you make minus 6.80? Add 6.8 to everyone. So when you add 6.8 to everyone, now suddenly u of infinity becomes 6.8 eV, right? And this potential energy becomes 0. Remember, kinetic energies are unaffected. So this potential energy becomes minus 27.2 eV plus 3.4 eV. Kinetic energy is unaffected. Therefore, the total energy of the first orbit would be how much? If you add this, minus 6.8 eV. Minus 6.8 eV. Clear with this? So it's minus 13.6 plus 6.8. Again, not a difficult question, but this is how things will be. Clear? Any doubts on this? Next one. This is a good one, right? Let's see how you do this. First one, see, it's a trap. The problem now, the moment you see this question, you see white light, and the first thing your brain tells, boss, it is Balmer series. Because after that, your thinking goes off. Yeah, we stop thinking. So, right, Advait. So understand one thing. Passing through an hydrogen gas, now white light, meaning, so there's a simple way to put it out. If you look at white light, the lambda violet is around 4,000 angstroms. That is your most energetic photon. So energy of a violet photon will be 12400 by this thing. So that's be around 3.1 eV. Getting it? And now in a hydrogen atom, which is in the ground state, the electron is in the first orbit. And for a transition, you need at least a 10.2 eV. That means we need ultraviolet. We need UV, right? Which is actually Lyman series. Getting it? But how much are you giving? You are giving 3.1 eV. So will the electron ever excite from 1 to 2? It will never excite. Nothing will happen. There will be no this thing. Suppose if the electron had been in n is equal to 2, right? And then when you send visible light, then it will be excited from 2 to 3 and 2 to 4. Are you getting it? So visible light, this is useful. So white light can excite the electrons from n is equal to 2. But in a hydrogen atom, the electrons are in the first orbit. For that, you need ultraviolet. I hope you're getting the difference. But the moment you see the white light, you get a feeling like, oh, Balmer series. Right? So we can write that also. So if you see the Balmer series, which is the visible light, can excite electrons from n is equal to 2. But there are no electrons in n is equal to 2. Now, what about the next one? Now you will see the relation between them. If radiation of all wavelengths from ultraviolet to infrared is passed through hydrogen gas at room temperature, absorption lines will be observed in Lyman series. I hope you can see the relation between them. So that hydrogen in the ground state will absorb only Lyman series. But once it excites, while de-exciting, it will emit Lyman, Balmer, whatever you want. I hope you're getting the difference. So don't get confused between both. Next one. We have a hydrogen atom. N is equal to 1, N is equal to 2. So this thing is a fixed atom. The electron, when it excites from 2 to 1, it emits a photon, lambda. In the second case, this hydrogen atom is free to move. And again, when the electron excites from 2 to 1, for some reason, you got a different wavelength. An electron transitions from 2 to 1. Right, in two different ways. Case 1, it's a fixed atom. Case 2, the atom is free to move. And we observe the wavelengths are different. First, you need to think why the hell the wavelengths are different. So find delta lambda, which is lambda dash minus lambda. Exam the simpler question would be this, which is greater, what is the relation between lambda and lambda dash? They're equal, lambda is less, lambda is greater, and so on. Find delta lambda minus this. So assume delta lambda is much smaller than lambda dash and lambda. So it's a very small quantity. And mh is the mass of hydrogen atom. Let's see how you handle this. So there's a very small difference in wavelength. Try, I'll give 3-4 minutes. First, figuring out is the important thing. Why the hell the wavelengths are different? Start from there. Let's see, why is the wavelength different? In the first case, this is a fixed atom. So whatever energy you had, energy of this thing, E2 minus E1, which is around 10.2 eV, is nothing but hc by lambda. But when you're free to move, the problem is this thing is like firing a gun. This hydrogen atom will also get a velocity Vh. So initially the system is at rest, linear momentum is conserved. The hydrogen actually moves back. This is your recoil speed. Therefore, so initial momentum is 0, then h by lambda dash minus mhvh. So the energy of the photon, E2 minus E1, which is 10.2 eV, which is still the same, but now it is shared between two things, which is hc by lambda dash plus half mhvh square. So from here you can clearly see lambda dash is the energy of the second photon is much lesser than the energy of the first photon. Therefore, lambda dash is greater than lambda. This is the reason you get a small discrepancy in wavelength. Right, from here, now if you try to play around, this thing will be hc by lambda is equal to hc by lambda dash plus I will write this thing as momentum square by 2 into mh. And this is a momentum, which is nothing but h by lambda dash. After this is all math. That will be h square by 2mh lambda dash square. H goes off, and we also know delta lambda is nothing but lambda dash minus lambda. So let's replace lambda dash everywhere with delta lambda plus lambda. This is c by lambda, this is c by lambda plus delta lambda plus h square by 2mh lambda plus delta lambda square. Since delta lambda is very, very small, I can use binomial approximation. Take out lambda common, and this will become 1 minus delta lambda by lambda. This will be h square by 2mh lambda. This will become 1 minus 2 delta lambda by lambda. And there, you can simplify this. You'll end up with delta lambda here. That is the thing about delta x is much, much smaller. Use binomial approximation, and from there, I think, yeah, then it becomes easy to solve. Get all delta lambda to one side and finish it off. Clear with this? Actually, if you see, this term and this term will cancel, you would get a decent answer only. Conservation of momentum. Question should be of this sort. Like I said, a simpler mains level question will be which lambda will be more. Yeah? Any doubts on this? Next one. Let's say in a hypothetical atom, force between nucleus and electron is given by F is equal to minus K by R power 3 by 2. K is constant, negative sign indicates attraction. Bohr's theory is valid. Find radius of the nth orbit. Let's see. Yeah, can you always go back to the basics? So if you have the electron, the attraction force will be K by R power 3 by 2. The centrifugal force is mv square by R. This is equation 1. Since the Bohr theory is valid, MVR is equal to NH by 2 pi. That is your second equation. You have two equations, two unknowns. So V is equal to NH by 2 pi MR. Take this and dump it in this. This will be K by R power half. This will be Mn square H square by 4 pi square M square R square. This would be R power 3 by 2. N square H square 4 pi square Km. You're done. So if they ask you R is proportional to N to the power of 4 by 3, they would ask this kind of question. Then R is proportional to what? Clear with this? Yeah. Easy. Next thing. The next one is important. Non-standard Bose model. This, you can say theory or an advanced paragraph. We will simply call it as a non-standard Bose model. So let's say if the mass of the nucleus and the mass of the electron is comparable. If you remember in Bohr's theory, right, there is one big assumption that the nucleus is at rest and the electron is going around. But if the masses are comparable, what will happen? If mass of the nucleus, Mn, is comparable to mass of the electron, Me, right? Then assume Bohr's theory is valid. Find the radius of the nth orbit. So let's see a little more context. Exam method, they won't explain all this story. They'll simply say this and leave it. But let's see what happens exactly. The first thing that happens, since the radius of the nth orbit, energy, radius, energy, and Rydberg constant. Right? So the first thing that happens here, since masses are comparable, they will rotate about their common center of mass. Binary star system. You guys remember this? Masses are comparable. They rotate about center of mass. Binary star. Mass of the nucleus, mass of the electron. Agreed, the center of mass will be closer to this guy. The nucleus will go in a smaller circle, electron will go in a bigger circle. When here is a radius of the nth orbit, we are talking about the distance between them basically. Because both are going in different radiuses. So calling it radius doesn't make sense. So after some time, nucleus will come here. Electron will come here. So this is how they rotate. Right? Basically, if you remember in standard model, nucleus is at rest. So whatever we derived, everything was under the assumption nucleus was not moving, which is kind of true. There will be very slight differences. So how do you approach this? Try. I'll give 2-3 minutes. Let's see. Hmm. Electron has a finite radius. Yeah, let's not go there. Electrons are already very small. The radius is only very small. You can still work. You can treat it as a point particle only, because spheres are special. A sphere can be treated as a point particle and can be solved. So it won't matter. So now look at this thing. Yeah, we get something called a reduced mass here, but how did we get that? Because if you don't realize how you got that, tomorrow someone will say like this: we have a nucleus and there's an hypothetical particle and an electron. All three are going in circle. Then what will you guys do? Right. So you should know how you derived it instead of, in case you know how to do it, then great. So let's see. So we have Mn. We have mass of the electron. So center of mass is somewhere here. This is going in this circle. This guy is going in this circle. Let the distance between them be r. Let this distance be r1 and let this distance be r2. We know the center of mass will divide them in the opposite ratio of masses. So r1 will be mass of electron into r by Mn plus Me. Similarly, r2 will be mass of nucleus by Me into r. Now, if you look at the forces on the particle, these things will be attracting due to k z e square by r square, the electrostatic force. The centrifugal force will be mass of an electron into omega square r2. You could have taken the other one also. So if you equate the forces here, you end up with k z e square by r square is equal to mass of an electron omega square r2. Or this can be also written as mass of the nucleus omega square r1. Omega will be same for both of them. Both are right. Right? So, and then if you try to equate this, so this is the force between them, kZe square by r square. Mass of the electron omega square r2 will be mass of the nucleus r by Me plus Mn. So you can clearly see the force of attraction is given by mass of electron, mass of nucleus by mass of electron plus mass of nucleus into omega square r. This can be replaced with a reduced mass mu omega square r. You're just replacing that whole thing with one term called mu. We'll see what it is. But if you remember, we have used this before in different chapters. Okay, we got something like this. So the next thing, angular momentum is quantized. So this is what I said. Now, if you use MVR is equal to NH by 2 pi, you're taking MVR of whom exactly? So when you say angular momentum of the system is quantized, mass of the nucleus, velocity of the nucleus, radius of the nucleus, plus mass of the electron, velocity of the electron, radius of the electron is NH by 2 pi. You're getting it? Because in the standard model, nucleus is at rest, the first term used to become 0. Hope you're getting this. So if there are 3 particles going, then you have to take the angular momentum of all the 3 particles. Hope you're clear with this. So that will change in this question. Now here, if you try to arrange the numbers again, so this is Mn. V is nothing but r omega, so that would be r1 square omega plus mass of electron into r2 square omega. If you again substitute r1 and r2 ka value here, you will end up with Mn Me by Mn plus Me omega r square is equal to NH by 2 pi. Again, this can be written as mu omega r square NH by 2 pi. So you will notice something here. These mathematical equations are behaving as if, so the two equations which we saw, the force and this angular momentum. So we are manipulating them now. The equations look similar to a standard Bohr's model. The only difference where the mass of an electron is replaced by the reduced mass. So this is how you can remember this when they ask you non-standard model. So simply you can make the question like this: take the nucleus, keep it at rest. So you're getting back your standard model again. And we have an electron which is going in a circle, but this time it's not an electron, but a particle of reduced mass mu, which is going in a circle. And if you solve the problem for this, you will get the same answers as a non-standard Bohr's model. This distance is r, which is the distance between them. The charge is E and mass is mu. Is that making sense? So the mathematical equations are telling you, if you replace the mass of an electron with mu, and if you try to solve it like a standard Bohr's model, the answers which you will get will look exactly same as a non-standard Bohr's model. So there's no need to solve. You can just replace the whole thing and finish it off. Clear with this? So if something like this pops up, so you need not derive all this stuff again, like I showed you. You can directly do this thing, replace with reduced mass and finish it off. That is how you got this. And you need to know why you got this, because tomorrow what will happen? They will create something hypothetical. They will say, we found a weird atom where there are two nucleuses and there are two electrons and all four are going in a circle. And they'll say Bohr's theory is valid, find the radius of the first orbit. You will be gone. You'll be like, what the hell is happening? Right. And then but if you know the story, right, you will see the same thing. So binary star system. So this force, and this force is making it go in a circle. Angular momentum is quantized. That's it. We always get two equations only. Getting it? No matter how complex you make, whatever you want to mess it up, you'll always end up with this only. Now, coming back to this, so we have to replace R with that. What is the radius ka formula? H square epsilon pi me square. So for a standard model, we know radius is equal to h square I'll do one thing. You can clearly see R is proportional to 1 by m. That is better. I'll write that. So basically, if you see the radius of the nth orbit Rn is proportional to 1 by n, 1 by mass. Right? What about energy? That's what I said you should know. It is proportional to what? The energy is proportional to mass m. Energy of the nth orbit is proportional to mass of the electron. The Rydberg constant. The Rydberg constant is also proportional to mass m. Therefore, in the new non-standard model, let Rn dash by Rn will be 1 by mu in mass of electron. So Rn dash will be mass of nucleus plus mass of electron by mass of nucleus into the radius of the nth orbit. This is your standard model, which is that 0.53 angstroms and all that stuff. That is the standard model ka radius. One plus me by mn into Rn. So you can clearly see the radius is actually increased. Similarly, energy will be En dash. En will be mu by mass of electron. So energy of the nth orbit in this non-standard model will be mass of nucleus by mass of nucleus plus mass of electron into, you can say again, energy has actually decreased. And the Rydberg constant R dash by R also will be same thing, mu by me. So the new Rydberg constant will be Mn by Mn plus Me by R. So if you make mass of the nucleus much, much greater, you will notice they'll become equal, isn't it? If you put Me tending to 0 or if you put Mn tending to infinity, you will get the non-standard model becomes the standard model. Clear with this? Now, and this is how they'll frame a question on this. So instead of telling you all the story, if they ask a question of this, you'll be gone. If an electron jumps from n is equal to 2 to n is equal to 1 in a hydrogen atom, 1H1, and deuterium atom. Deuterium is also isotope of hydrogen, 2H1. Whose wavelength is more? Most people will think, yeah, what difference does it make? Both are hydrogens. There's one extra neutron, so what? Now, people who don't know the standard Bohr's model, they'll not understand what the hell is happening. Can you tell me what is this? If you remember that formula for 1 by lambda, 1 by lambda will be Rydberg constant into 1 by n1 square minus 1 by n2 square into z square. Nothing changes here. So we can clearly see here 1 by lambda is proportional to r. Right? And we know r is proportional to Me. So in the new standard model, 1 by lambda dash will be proportional to mu v. So we get lambda dash by lambda will be Me by mu e mu. This thing turns out to be how much? So we get the new wavelength in this non-standard model will be lambda into you can actually guess from here. You can clearly see the energy of the orbit also has decreased. So if the mass is more, so lambda dash will be lambda by 1 by there. This is the wavelength. So you can clearly see mass of deuterium is greater than mass of hydrogen. Therefore, mass of electron by mass of deuterium will be less than mass of electron by mass of hydrogen. Reverse. Therefore, if you see the denominator, reverse of this, so if this denominator is bigger, I think I wrote reverse here. I think I wrote reverse, wait. Okay, therefore, lambda deuterium should be bigger or smaller. If mass of deuterium is more, this is more. If this is more, this value is less. If this is less, the whole function will be more. The lambda deuterium is greater than lambda hydrogen. Clear with this? Let's just check this once. Let I goof up here. The Rydberg constant now it is there. So if your Rydberg constant is mn by mn plus me. I think I wrote reverse, kya? Lambda dash will be mu lambda is this. I wrote reverse now. This is mn me, so this will be me plus mn by mn. This is 1 plus mass of electron by mass of nucleus. Yeah, if the mass of the nucleus is more, then this thing will decrease. Therefore, lambda d will be less than lambda h. Basically, the deuterium ka photon will be more stronger, so wavelength will be less. Clear with this? Yeah, just recalculate the calculations. So this is how they'll frame my question. There'll be a very slight difference, but there will be a difference. So higher the mass of the nucleus, the more energetic the energy levels will be. So more energy levels, that means the difference in photon will be more. I think that's an easier way to remember. So when you jump, the photon also will have more energy. More energy means less wavelength. Clear with this? So here you can clearly see the energy is proportional to mass. All clear with this? So yeah, that's your non-standard Bode's model. So next class when we catch up, we'll continue from this. We also have something called atomic collisions. So you saw gravitation ka binary star now. Next we will see collisions in this. Right, and we will see 1 or 2 models on this, and then we will go ahead with X-rays. So like I said, you will see the concepts will be very small, but you can see a lot of weird varieties. Okay, with that we'll wrap up for that day, and I hope everyone has given the test. If there's a deadline till tonight, so make sure to give it. So any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you guys again next week. So take care, stay safe.